All right, so now let's look at another example, and let's call it example 2. All right, so in this example 2, we are still going to evaluate. We still want to evaluate logarithms. And ideally, I still would like anyone learning from this lesson can still be able to go through this example 2, every single problem of example 2, where we evaluate a logarithm, but completely without a calculator. Okay, so ideally that's the plan right there. I would do this myself on the board right here in front of the camera without using a calculator, so that after learning through this example 2, you will sharpen your skill of how you can use your past algebra understanding into evaluating a logarithm operation. Okay, so now we're going to evaluate, and again, let's try to go as much as possible, as far as possible in terms of without using a calculator. So part A. So now let's calculate, let's evaluate. So at this point, everybody anyone at this point learning in this lesson has been fluent with all the different notations and conventions of how we write a log symbol and a log notation. So now I'm saying this is a log base 6. That's how we read it out loud. We want to evaluate log base 6 of 1 over 36. Okay, log base 6 of 1 over 36. Okay, and so things are, of course, getting up the problems in example 2 here. The kind of problems are similar to example 1, but each problem itself is getting a little more advanced, that requires more critical thinking. Okay, and so every little example problem I bring in here is an experience. I would like to pass it down to anyone learning from this video lesson right here. But once again, along with what I was introducing earlier in the lecture over here, a logarithm is a question. So when we're reading this notation, yes, we read it out loud, log base 6 of 1 over 36, but behind the scenes, in the back of your mind, we think of that question: what power of base 6? Base 6, we're reading it log base 6 of 1 over 36. So we think of that question, and we're trying to look for that answer. What power, that's why I'm leaving it an empty box right here, what power of base 6 to equal 1 over 36? All right, what power of base 6 to equal 1 over 36? All right, and so in that way right there, then our mathematical mind can tell us, and without using a calculator, some of our algebraic understanding from the past courses will come back and have good pay here. Okay, have good payback here. All right, so I realized algebraically that, well, it's just a little bit of a thought process right here. 1 over 36 can be thought of as the 36 in the denominator here is really a 1 over 6 squared. I start seeing the 6 right here. That's just a thought process. And then I can think further. So hey, maybe 1 over 6 squared is the same as a 6 to the minus 2, because it's in a reciprocal form. So that means we can rewrite it as a negative power. See? It's all of the algebraic experience we've had from our past courses there. All right, but now wait a minute. This is now base 6, and that power is there. So it looks like we all of a sudden realize we found our answer, negative 2. All right, so with so much thought process, but primarily we focus on looking for an answer to this question. What power of base 6? What power of base 6 to equals 1 over 36? Now we found our answer. Our answer here is now legally or officially minus 2. That's how the thought process is laid down like that. So this is just a thought process. You can think of that as scratch work, but as a goal, primarily as a goal, answering this question in evaluating a logarithm, again, I just repeat that thought process. Right? That we first think of that as find our way to answer this question: what power of the given base to equal this number? And then from that point on, we start laying down more thought process. And I went completely without a calculator. I only relied on the past algebraic understanding that we've had from our past courses. All right, so in that way, let's look at part B of the example. All right, so part B of the example. Let's look at how about log base 5 of cube root of 5. Okay, log base 5 of cube root of 5. Okay, so like I said, I sincerely apologize to anyone if you feel that I'm slowing you down, but again, allow me, in any of my lecture, allow me to move on at the pace where, even with the learner who is at the minimal math experience can still follow through like that. Okay, so if you feel like I'm going fast, I'm going too slow for your own pace, as you are watching this video, feel free to fast forward if you would like to. Okay, so now again, this is a logarithm. As we read it out loud, this is log base 5 of cube root of 5. Okay, and then in order to find the answer here successfully, we think of this question right here. What power of base 5 that equals cube root of 5? That's the question that we want to look for the answer. Okay, it's the question that we want to look for the answer. So think of that question, and then we're going to start looking for the answer. The answer to this question will be the answer to this logarithm evaluation problem right there. All right, and so now very similar to the earlier problem in part A that I brought up right there. And so now let's lay down some further, thought process. So cube root of 5. In our experience up to this point, working with algebra right here, then a root, an nth root, a square root, a cube root, a fourth root, a whatever nth root in general is regarded as a fractional power. Okay, a power as a fraction, or an exponent as a fractional exponent. All right, so now it's so clear that cube root of 5, as in my thought process, I think of that as a base 5 to the 1/3 power. Base 5 to the 1/3 power. And all of a sudden, we realize we've come to the answer. The answer is here. What power of base 5 that equals a cube root of 5? That power is here. All right, so now answering that question, what power? It's power 1/3. And so now we officially come to the answer to this log base 5 of cube root of 5. That's 1/3. And one more, that's another problem where I've done it completely without using a calculator. And of course, I already laid down a lot of thought process in there, so it took sometimes, okay, maybe 5 minutes, 6 minutes, or it could be up to 8 minutes long, okay, for one little problem. But the point now is that once you are fluent enough and carry it on your own right there, it should be a lot faster than how I'm doing it up here. Okay, because once you and these skills right here, the more you're working on that, right, the better it will build and the faster it will come. Okay, when you're doing these problems. All right, so now let's look at another one. So in part C, all right, so log 0.0001. Okay, log 0.0001. So now have a closer look. This log, I did not forget to write it. This log did not have a base indicated. Okay, it means it's log base 10. That's how we're reading it out loud right here. Log base 10. Recall for yourself that in what I have explained earlier, anytime the base is skipped, okay, that base indication is skipped, which is the case here, then it means it's log base 10. Okay, so this is log base 10 of this ugly looking quantity, 0.0001. All right, so now once again, in order to find the answer of this evaluation problem, in order to evaluate this logarithm of this log base 10 of 0.0001, we think of that question. Base 10, recall again. Okay, so base 10, we think of the question, what power of base 10 that equals 0.0001? What power of base 10 equals 0.0001? Okay, so now as a thought process, Okay, in the earlier problems, I was writing the arrow up here. I leave my thought process down. That's just a thought process. You don't even have to write this down in your own work if you have to show the steps. Okay, so think about the 0.00001 right here as a, this is really, I mean, naturally enough for anyone. I'm going with the routes that's most natural for anyone, that no one can argue about it. As I said, my approach here is to deliver the steps where any person with the lowest, I mean with the minimal experience in math can still follow through, that can still see what I'm doing and understand. So 0.00001, anyone is familiar with that as a 1 divided by, okay? All right, so 0.00001 is the same as 1 over 100,000. All right, and then in that way, this fraction, so this is like everybody knows, okay? And then with a little bit further of experience with powers and exponents, that's big number with 5 zeros at the end right there is the same as a 10 to the 5th power. 10 to the 5th power, okay? And so in that way, now similar to example A, part A I've done earlier, see, we have a power in the denominator. It's in the reciprocal form right now. So I think of this as a 10 to the negative 5. So now all of a sudden I realized something. The question that we initially tried or attempted to get an answer for, what power of 10, what power of base 10, what power of base 10 that equals this quantity. And we worked around, we laid down some thought process with this extremely small value right here. That is the same as a 1 over 100,000, and then that's 100,000 is the same as a 1 over 10 to the 5th. Okay, 10 to the 5th. All right, and then from there, 1 over 10 to the 5th is now, algebraically understood as a 10 to the negative 5. So all of a sudden, I realized that I have really found the answer. That answer here, what power of base 10 to equal this? The answer has to be power negative 5. Power negative 5. So we have found the answer to that question. So now all of a sudden we realize further that we have found the answer, the official answer for this logarithm. So log base 10 of 0.00001, okay, equals negative 5. Okay, so that's how I lay down the thought process like that. All right, and so now let's look at another one. All right, so part D of the example. So now we're looking at, and this is another good experience for anyone learning from this video lesson. Natural log of e to the minus 2. At some point, I have to make it clear that we don't need to make it any more complicated than it needs to be. Okay, well, the expression right here at first looks a little complicated or maybe unusual for somebody. ln, okay, log base e of e to the minus 2. I will put in the formal name of the special log right here in case I might have said that accidentally earlier. Okay, if you might have picked up some strange name I have used for that earlier, we will all come to a formal name for that. But anyway, right now, formally at this point or legally at this point, we call this the log base e of e to the minus 2. We want to find the answer to that. We want to find what's the evaluated answer for log base e of e to the negative 2. Okay, e to the negative 2. And then so this is equivalent to the question, what power of base e to equal e to the negative 2? We don't need to think, we don't need to overcomplicate the problem. That power is here, negative 2, negative 2. It's needless to say e to the negative 2 to equal e to the negative 2. So the answer here is 2. All right. I mean, The answer is negative 2. So, what's the intention of this problem? I didn't even have to lay down so much process, but the intention of mine when I brought in this particular problem is that sometimes, a lot of time when you're taking a logarithm, okay, log base a, and then of a number, whatever number that is, and then the whatever that number that is, but the number that we can bring that into the form that we can immediately see the number as in the form of the same base with the base of the log, and then raised to a certain power n, and the answer is simply coming out just quickly n, right there. Okay, which is in this case right here. This is log base e, and we realize immediately that the whole number that we're taking logarithm of, that whole number has already been expressed, or we can express that whole number, that entire number. I shouldn't say whole number. That may cause some misunderstanding. The entire value here, okay, the entire value inside of the log can be any time that we can find our way to express the entire value inside the logarithm as a power with the base being the same base with the logarithm, like that case right here, generally as a rule. Okay, and I will come back to this and discuss even more in more details with that. Okay, but then anytime we're looking at that, right, we can write our entire value inside the logarithm as a power of the same, of the base of a base that is the same with the base of our logarithm right here. See, same base, then the answer is simply just that number n right there. We don't even have to go through this thought process, and that's my point of bringing in this particular little problem, because it seems, I mean, at first it may seem a little unusual, because our mind is so, sometimes our mind is so stuck with that. We have to set up that question right there, but you know, we need to break free and be a little more flexible than that. All right, so here we picked up a little fast trick right here that helps us speed up the process sometimes. So if we think back, before I leave this example, if we think back of those earlier problems I brought in this example 2 right here, okay, then alternatively, another way of solving those earlier problems is as following. Okay, so here I'm just talking about an alternative way of presenting your thoughts, of showing down your steps, for example. So back in part A, so the way how I explained that earlier was for anyone who was really the first time being exposed to logs. That's how you can get successful. But now for anyone who is already a little more experienced, okay, the following way of presenting your steps should be fine right here. So for example, back in part A, okay, and we don't really, I don't intend to repeat the whole example, but there's a lot of details I would like to point out right here. The log base 6 over 1 over 36. Okay, so now as far as the formal steps, you can also think about it's the same as a log base 6, but then immediately re-express that value. Right now it's a value in fraction. Re-express that as a power of base 6. So now I recognize the base of the power here and the base of our log is the same base, and now we already express our entire value here as a power of that base agreeing with this base right here. Then the answer is simply just -2. That was what we've had in part A, but going with this route right here, it requires some more solid experience from your past courses. And this part right here was part of the thought process that I laid down. So I made quite a huge jump right here by skipping entirely all of that thought process I laid down earlier. So you're welcome to go this way, okay? If you feel comfortable with your math, your background, your experience in expressing a number as a power. But otherwise, going through the thought process like I've had earlier when I was formally presenting the problem, that'd be completely fine, okay? And so same way in part B, for example, we saw earlier the log base 5 of a cube root of 5, see? And so another way of thinking, just like according to that little trick I picked up right there, think of that entire value here immediately as a power. Well, right now it's log base 5, let's leave it there. We know, we just be aware it's a log base 5, but now I'm going to try my way. I'm going to make my way to re-express this entire value as a power of base 5, So cube root of 5, yes, as a power of base 5, it's power 1/3 of base 5. And now power agrees with, the base agree with the base here. Now the answer is just simply that 1/3. And once again, it comes agreeing exactly with that answer how I've had earlier when I was going with all of the thought process laying down like that. All right, so this is just an alternative method of how to handle the problem. And there's no need to repeat all of the other problems that we went through. All right. And so now, right before we completely leave example 2 here, now I am going to leave an FYT for everyone learning in this video lesson to try on your own right here. So FYT is for your own trying. So the idea is once I finish writing it down, you're going to have your own thought, you're going to spend your own thought process into it, and then I'm only going to tell the answer, the final answer. And then you feel free to pause the video, okay, to have a lot of thinking into the problem like that. Take your time for that. All right, so let's evaluate in this one right here. Log base e of e cubed. All right, so again, like I said, pause the video, spend your time as much as you need like that to get to the final answer here. Once you resume, I will only write down the final answer without any explanation. All right, so at this point, assuming you have already paused if needed, and had some time spent on this problem right there and laying down some of your thought process, the answer to this evaluation problem is simply just 3. Like that. All right. And so now, this is where we are completely done with example 2. All right, so the entire example 2 was simple in a sense that, see, was still okay in a sense that we can still use our own mathematical experience to do the work to perform the evaluation problem without using a calculator. Okay, and then later on it will come to a certain point in our time working with the logarithm that where we definitely need to use some technology, some calculating device, some calculating power, okay, to help us going through the problem. All right, so now before we get there, let's formalize a couple other naming and conventions like that. So now you have learned at this point that this ln symbol, okay, this ln symbol, for example, we can put in a value right here, ln of a, for example. So this is a value. So the way how I've been showing anyone learning in this lesson is, this is called log base e. That's how we're reading it out loud, right? That's how we know about it. So yes, one way of knowing it, and it's still the same, log base e. Okay, that's how we're understanding it, because as according to the convention, anytime it comes to base e, we skip the log. We entirely change the notation. We don't go log with the subscript e. We don't do that. We write ln, but ln is meant to be, or ln means log base e if we're reading it out loud. All right, but now this ln symbol, this log base e indeed has another name, and it keep getting better and better popularity. Right? More and more people are going with that name I'm about to show you. So log base e now in these days, not too many people refer to that. Not too many people read it as a log base e anymore. And you might have heard me accidentally saying this earlier already. Log base e, okay, is log base e is called. So this is a very popular name, now. The natural log, okay? It's natural log, okay? Or formally, it's a natural logarithm, okay? That's what it is, and just earlier I wrote in the short form the natural log when you were saying it verbally, because we don't want to keep we don't always want to keep staying with the long way of calling it natural logarithm. So just for short, natural log. Okay, and that's what ln is for. All right, and so that's just how we call it when we communicate verbally with other math students or math professors or math the experts or mathematicians out there. Natural log. Okay, that's the name for log base e. So similarly, we have already learned that for another one here, we have learned that anytime it comes to log base 10, okay, then we skip the base indication. Okay, so log base 10 of the value right here. So now this is yes, as we read it out, we read it log base 10, and that's how I've been showing, you know, in the earlier part of the video prior to this point right here. But now we legally have another name. We formally have another name. Okay, so log base 10 is also called, so this is another way of saying it. So I should have also say, you know, log base e is also called natural logarithm, but more people is regarding to that name right here instead of going with log base e. But then for the log base 10 right here, it's about 50% of people out there go with the name I'm about to show, and 50% of the people call it log base 10. Okay, there's not really a winner in that. All right, so log base 10 is also called the common log, or yes, formally the common logarithm, and for short we call it common log. All right, so that's how we call these things. So it's anytime teaching the log, any instructor, any responsible instructor must show, you know, the way what it is, how it came about, and then what's the other name of that, because it's all for the communication purpose. Okay, and so starting from this point on, in any of the later part of the lecture, either in this same lecture or some other later video lectures that I post, if you hear me using the term the natural log or the common log or the log base e or the log base 10, you know which one is the same with which one, and you will know exactly what I'm talking about. I'm going to use these terms interchangeably, okay, throughout all of my lectures, starting from this point on. All right. So in that way, after we have now picked up the name right here, let's get everybody who learns in this lesson into another example. Okay, so let's look at example 3 right here. We have already seen some demonstration prior to this point when we get to example 3, but now I want to bring up this short example to remind anyone about what I brought up earlier, and then formalize that into a certain number of steps like that. Okay, but so the whole intention of example 3 now is that we want to use let's say we want to use a calculator. Okay, use a calculator to evaluate. Okay. All right, so now part A. This is the common log or log base 10 of 1045. Okay. See, the instruction is saying it clear, use a calculator to evaluate it, and to evaluate this value right here. So think about it. There's a reason why we are asked, I am asked, or you are asked to use a calculator, because with something like this, it's impossible for us, for the human mind, to come up with a power. So ideally, this is about, yes, what power of base 10 that equals 1045. But now, back to what I was in the middle of saying earlier, it's nearly impossible for a human mind. Okay, my mind, your mind, unless, I mean, there are still students and professors out there with minds, with their minds 100 times more brilliant than my mind right up here. And so they may find a way to mentally calculate that power. But then for a bigger majority of people where I belong to, then it's impossible for me to find that power. So we need to look over to a calculator and looking for some help from a calculator. So we ideally we know what we're doing, but we need a calculator to help us figure out what that power is. All right. So now in that way, I'm gonna head over to my computer station right there and turn on my calculator simulation like that. Okay, so throughout all of my lectures here for this course, I'm using the TI 83 or 84 calculator. okay, to show all of the calculation work. But in case you are using a calculator other than this one I'm using right here, then you just have your own responsibility to read your own instruction manual for that. Okay, so all right, so now on my TI 83 and 84, so the software I'm using here, the actual version of the TI 84 I'm using here is the TI 84 plus CE, but any other TI 83 or 84 on standard out there will function exactly the same way. All right. So now we want to calculate log base 10 of 1045. And so I've mentioned this in some of the demonstration earlier, that this calculator I'm using and it's quite the same with any other calculators out there, not only in the TI family. For any calculator out there, there will only be 2 buttons for calculating logarithms. One button is for the log base 10, okay, and the other button is for the natural log. Okay, one button is for the common log and one other button is for the natural log. Okay, so before we get further, allow me to quickly explain the reason why, and I'm saying it's not only something that's happening to the TI family calculator, but it happens to the Casio, it happens to the HP calculator, any calculator being sold on the market out there. I highly believe, and at a very high chance, it only has at the most 2 log buttons only. One of them is the log base 10, and the other one is the natural log button. Like that. Okay. Why is that? Simply because, think about it, we have so many logs out there. And our journey in learning about the logarithms just began not too long ago. And you have already seen there are way too many logarithms out there, because as soon as we change the base, there's log base 2, there's a log base 5, there's a log base 3, you have seen log base pi in my demonstrations earlier, there's log base 0.5, there's so many bases to a logarithm. And then back to what I was saying about our journey with logarithm, we just began not too long ago. So of course at this point you have not learned much about how similar all logs, regardless of what basis they are. Okay, but all logs will behave quite similarly. We will get to that point, and for that is the reason why on any calculator. Okay, so if the engineer who designed this calculator designed to put in a log base 2, aside from log base 10 and natural log here, then log base 3, log base 5, and all the other logs are going to complain. Because how come you also include log base 2 but you don't include us? Okay, or if we put a log base pi here and skipping out a log base 2, log base 3, log base 5, all the other logs, we also complain. Okay, so the engineer worldwide, and that's the reason why we call this is common log, okay, and this is natural log. They do have the most the number of applications out there. That's why all the engineers who designed these calculators have decided quite worldwide that they only put 2 important logs here, 2 most commonly seen logs, okay, natural log and the log base 10 right here. Okay, so any other log and any logarithm on the other bases, at some point later on in the lecture I will have to show you how we can work around with those. There will be a workaround, but there won't be on any calculator, on any standard calculator, there won't be a direct button. Okay, a direct button to calculate a log with any general base like that specifically given. All right, so there will be a workaround, and at some point, either in this lecture or in some other later video lecture that I post, there will be a point where I'll show you, any of you learning from this video lesson, about that. All right, so now back to this problem. So I'll go again. For part A of the example is to calculate log base 10 of 10045. So now, once you have a clear understanding about where to look for your feature like that, then now it's just that button. We click on that once, and it's as a command base right here, it's already popped out log, no base indication, and then with an open parentheses here. All right, and then this is the reason why I said earlier that if you are using a calculator other than the version, other than that calculator I'm using here, then make sure you read your instruction manual, because the order of operation may be a little bit different with some of the other calculators. It's just, I never had time to find out the reason why some engineers design their calculator different with the other calculators. Okay, so now with this way, how this calculator runs. So now it's just like how I wrote on the board earlier. This is a log, the base 10, so it opens a parentheses. And now all we do is just simply enter that 10045 in there, and now close the parentheses. And now this syntax right here, as we completed it, looks just like how I wrote things on the board so far throughout the entire lecture so far. Now we hit enter. All right, and that is now our answer right here. All right, so now it's a 3.019 right there. For lecture purpose, I'll just go with the 3 decimal places rounding, but do aware for any other rounding requirements when you're working with problems outside of the lecture like that. All right, so now we've found our answer. Okay, 3.019, and as I said, it's just for my lecture. Normally, when it comes to log, I round to 3 decimal places, but anyone learning should be watching for your own rounding. Should be watching for the rounding requirements on your own problem on each problem. Okay, now we're ready for another one. Okay, it took me so much to explain the first one, but now with starting the next one here, things will get a lot faster. All right, so now part B, and here we can really pick up the pace here. So how about natural log of 0.02? All right, it's another problem where if we try to use our mental math capability, then, well, at least for me, I would say good luck to myself. Okay, but because, well, we know that it's log base e. I just now said natural log, but this means what power of base e to equal, and that can equal 0.02. Okay, but now finding that power, that's why I was saying it earlier. Even to me, I would say good luck. Okay, and this is why we need the assistance from the calculator. All right. All right, so now on the calculator screen here again, the log, the button designated for natural log is here. So I'm going to go ln, okay, and the syntax is going to be exactly the same like how I was using the problem for part A earlier. So now 0.02. All right, now we close that parentheses. All right, and hit enter. So now our answer comes out being minus 3.912. All right, minus 3.912 because I decided to round to 3 decimal places. All right, so now that answer there is approximately, and I should have also used the approximation sign for the earlier problem as well, because it's not the exact problem, but it's close enough. All right, so minus 3.912. All right, so that's approximately our actual answer to that. All right, and we can check, and I should have done this with the earlier problem as well. We can check for consistency as well. Okay, so you see this is this final value here is a 0.02. We want a power so that E itself is a 2.718. Have that recall in your mind right there. Okay, E itself is a value greater than 1 already, quite greater than 1. So and then here after the power, it needs to, the requirements here, it needs to be 0.02, a very small value. And so needless to say that it makes sense that the power got to be negative. Okay, and so that's how I check for consistency. And so yes, negative 3.912 is what it is. I want to create that clear understanding that even though we use machines sometimes here and there, but we definitely don't want to let machines take over our understanding. Okay, because in the end we created machines, right? And we got to know how to drive it. Don't let the machine drive us. That's why somewhere here and there I keep showing the different way to check for consistency whether we have driven our machines correctly. All right. That is how we've done with example 3. That's all there is. And then I don't think there's even any need for coming up with an FYT here. It's just really only intent for showing how you can use any technology, okay, to calculate these logarithms here, the natural log and the common log. All right. So with that with the experience we have learned from example 3 right here, there's now starting to be a usefulness. So now we're done with example 3, and let's head on to the next detail I want to share right here. Okay. So back to what I was saying earlier. I haven't seen any calculator being sold worldwide out there that has a specific log for log base 2 and a log base 5 or a log base pi right there, because if the engineer design, think about the logic that way, if the engineer design a button for a log base 2, then he would have to also design a button for a log base 3 and a log base pi and a log base 5 and all of those are existing logs out there, which is impossible to fit all of those on a keypad. Okay, and because if the engineer only design a one button, all the log of the other bases are gonna complain. Okay, and so in that way, what's the workaround? I mentioned about that workaround right there, because in the end we only know there's a natural log button on the calculator. There's only the log base 10, the common log button on the calculator. Okay, that's the most we can see. Some loggers in the older days right there only have one button, the common log, back at that the older day right there, or some other calculators in the older day only had the natural log button. Okay, so what's the workaround I was talking about? Because in case we really have to calculate, for example, in case I really need, or we really need to calculate log base 5, not the natural log, not the common log base 5 of 75, for example. Okay, how are we about to do this with the calculator? Because problem like this will be quite common throughout a lot of our works later on. All right, but again, sadly, there's no direct log base 5 button in the calculator. So how are we going to get this? And of course, with something like this, we need a calculator, because yes, we know that we're looking for what power. That's what we're trying to look for. We're looking for that answer of what power of base 5 to equal 75. But sadly, our mental math capability is not strong enough, okay, for that. And it's not necessary to push ourselves to overcrank ourselves for things like this. Okay, so that's where we need the assistance of the calculator. So we theoretically understand the goal of our work, but then in the end, to use this in the calculator allow me to do the following. All right. So on the calculator, this is the workaround right here. And now let me clear out my screen right there. Okay, so as you already knew, there's no direct button for log base 5 and anywhere found in here. So now in that way, here's a workaround. We can make a choice. Well, for now, let's pick that choice going with the log base 10 or the common log right here. So this is what I do. So, and I said earlier, this is clearly just a choice right there. So to calculate log base 5 of 75, I'm doing this. Log base 10 of 75 seems like a shock at first, okay? But of course, I'm not finished yet. This is a workaround, as I said. So I'm starting out purposely with a log base 10, okay? It's one of the two logs that are already available here on my keypad right here. With my calculator, I go with log base 10 of 75. And then after that, I have to divide, okay, by, if I made my choice, once I made my choice to go with log base 10, I'm going to use log base 10 again. So log base 10 of 75 divided by log base 10 of 5. So think about where the two numbers 75 and 5 came from. 75 came from the value that we're trying to evaluate the log out of. And then the 5 that we saw on the calculator screen is from here. So according to that syntax I was doing, so since I'm still here with the board, the syntax was already describing the workaround solution. One choice, you can go with the common log. Okay, log base 10 of 75. And we divide that by log base 10 of 5. So the 5 here comes out from that base. The 75 comes out from that number right there. Okay, but and I went with log base 10 here as a choice. Okay, as a choice. And then so now I don't think we need this anymore. So allow me to erase that. So or And I'm going to get back to that. So let's now complete that calculation with the calculator, and that's the workaround right there. So now on the calculator, all we do is just hit enter. Simply hit enter, and this truly is our answer now. So approximately 2.68 and rounded to 3 decimal 3. So 2.683. All right. So approximately log base 5 of 75 is 2.683 right there, rounded to 3 decimals. All right. So when I was showing this earlier, and of course, at this point, I sincerely apologize for anyone viewing this lesson, either my students or public viewers out there. I have to sincerely apologize because at this point, that is one big explanation that I still owe you at this point of why or what allows me to do this. Okay, so consider that as something that I, at this point, I apologize in a way that I showed a way, but I could not point out an explanation why yet. It will come, okay? So I owe you that explanation of how or what rule allows me to do this. Okay, and later on we will get to that point where I will be able to pull back this quick demonstration, right there, this little demonstration, and then point out how how that explains for what we're doing here right now. All right, but then this is the final answer of log base 5 of 75 right there. So earlier I was saying log base 10 here was chosen as a choice or was picked as a choice. That means the same setup right here. I could have done the other way. I could have done in an alternative way. I could have gone, recall that calculator screen up when I was still on the calculator earlier. I could have gone with log base e or natural log of 75. So the structure remains the same. We go, once we have made a choice of the log to use, right there, either log base 10 or natural log, we have to go with the log of the bigger number first and divide it by log of the base in the denominator. So here it's log base 5. That's how we're doing it. Okay, so that's why I'm putting a big or here. We can go with this or we go with that. But see, only one log. Okay, only go with one log. Either way is going to get us that answer. Okay, let's verify it out right there. All right, so yes, just like what I wrote on the board, I could have picked natural log and then go with 75 inside a log and then divide. But I have to, if I decided to go with natural log, I have to stick with natural log. So natural log of 5. Okay, the answer comes out exactly the same, decimal to decimal. All right. And so at this point right there, that's the calculator workaround, okay, for any one of us who needs to work with a logarithm problem other than base e and base 10 right there. Because again, the only problem is that our calculators will always be limited. Any calculator we're using will always be limited to either just, at the most it's 2 logarithms, the common log and the natural log. Anywhere else is any other even more basic calculator will have just 1 logarithm, okay, either the natural log or the common log. Okay, so in that way, when we really need to use a calculator and get to calculating a general log like this, other than log base e and log base 10, we have to use this workaround solution, but we only need to pick one. All right, so in that way right now, at this point, once you have seen that calculator trick right there and have a clear understanding, we are ready for another example. Okay, so let's now call that example 4. All right, so we still want to, in this example 4, we still want to rely on technology, okay, to assist us in calculating the value of a logarithm. All right, so we want to use a calculator, right, to evaluate. All right, to evaluate. So now part A. So now things can start speeding up right here a little bit. So here I just want to show the the routine steps right here. So log base 3 of 0.75 right here. Okay, so let's see how we can calculate that. Of course, as far as a mental understanding, this means mentally we think of that answer. We think of that question. What power of base 3 that can equal 0.75, and then we use the calculator to look for that answer right there. All right, but now really, as far as mental math, it's hopeless for us here. All right, so now I'm gonna turn over to the calculator at my station, my computer station right there. Okay. All right, so with my calculator, so now log base 3 of 0.75, we can choose either one of those. So I'm more comfortable with ln as a matter of fact. So ln, because it looks shorter as well when I have to write it on the board. So I'll go with ln of 0.75. Okay, and then we're dividing that by ln of 3, because that was log base 3 of 0.75, and that's how I'm doing it. All right, and so now I hit enter, and that's the answer right there. All right, and again, I'm simply going to just go with 3 decimal places. So negative 0.262, even though the answer that you have seen on the computer screen was a lot longer. And this problem was just, as a matter of fact, this problem was only intended for you to get comfortable with how we work around with the calculator. So I really have no intention that we have to show any fancy written steps at all. And that's just the answer. The steps is just how we get through the calculator. Okay, and then you can, like I said earlier, you can either go with the log base 10 or the log base the e right there. Okay, but whichever log that you've chosen, make sure numerator and denominator there have to be the same logarithm. That's all there is. All right, so let's try again. So now in my next one right here, in part B of the example, let's look at log base 0.5. See, and then once we have learned that calculator trick, all of a sudden we feel like we are empowered with that flexibility. Okay, we have that flexibility that can help us reaching to any logarithm problem. Okay, so even base 0.5, I mean, it's not something that we commonly work with, but it's completely possible to get things done with a log base 0.5, because the base is positive and other than 1. Okay, so now log base 0.5 of 3. We want to find out what power. We want to find out, or at least approximately, what power of base 0.5. Okay, that can equal 3. That's ideally what we're looking for, but the answer has to definitely be an approximate only. All right, so again on the calculator, this time, how about let's switch to using log base 10 right here. Just want viewers and students of mine to experience different thing, but they all gonna get you the same answer. So log base 0.5 of 3. So I have to go now log base 10. I chose log base 10 to work with, and then and actually I put 3 in first. So log base 10 of 3 divided by log base 10 of 0.5. All right. So now we're gonna hit enter. And that's the answer right here for us. Okay, so negative 1.545 after rounded to 3 decimals. All right. Negative 1.585 after rounded to 3 decimals. All right. And so approximately negative 1.585 after rounded to 3 decimals, but the actual answer is a lot longer than that. Okay, all right. So that's what we have. Everything we have with the calculator trick right there, and how we can help us. It can help us with moving on to these through these problems where we calculate a log. Okay, so now we're done with this example. Let's head into another detail right here regarding the logarithms. All right, so All right, so now back to this equivalence. This was part of that definition I wrote down earlier in the earlier part of our understanding about logarithms. This was part of that what I was writing down about the formal definition, the core, the biggest part to understand about what a logarithm is. And so back to what I said earlier, see, if y is the answer to that question, because this whole thing here is a question. Log base a of x, that's how we read it, but it's a question. That's how I started introducing. So it's a question that what power of a, what power of base a that can equal x. And so if y is the answer to that question, then in my explanation earlier of the definition, it means so this double-headed arrow means that you can understand that as it means, okay. In some more advanced course in mathematics, you will learn about the actual logical meaning of this. But for now, it's just the double-headed arrow says it means. So if we're saying that y is the answer to that question, what power of a to equal x? If that answer is y, then it means a to the y power equals x. So at this point, it's needless to keep repeating and repeating over and over with that. Okay, it's so clear. But now, if we're looking at this equivalency, okay, in the two statements right here, then in the end, this is an equation. Before that, the meaning. So these are two separate statements, but they mean the same. Basically, that's another way I would like to point out right here. These are two separate statements. This is say, hey, the question, what power of a, what power of base a to equal x has answer y. It's one statement. But then it also means as another statement saying a base a raised to power y equals x. Okay, two separate statements, and they have equivalent meaning. That's why, like I said earlier, this statement means the other statement. Okay. And so now allow me to push that understanding into a further, in this direction right here, into a further understanding. So now as you clear with me that it's a statement, then yes, I see a statement here is written as an equation. This is an equation. I underlined that statement in red ink and I pointed out, yes, this statement is an equation. Like no doubt about it, because it has equal signs between two expressions. This expression on the left-hand side is a question, and the answer equals to this value. Okay, so it's an equation. But now this equation here, it's just now the way how we're calling it. This statement is an equation in logarithmic. That's how I'm saying it. That's just simply the way we say it in logarithm or logarithmic form. All right. This statement, the whole in the whole equivalency right here, that statement on the left of the double-headed arrow is an equation. We see that now as an equation. We view that now as an equation, but an equation in logarithmic form. Okay, and I wrote that term right here in red ink to hopefully catch your attention, so you can take notes on that in case you do decide to take notes. So that's one statement as an equation, and so now we call that it's an equation. This is an equation in logarithmic form right there. Because now really you should have realized that throughout all of the examples, including all of the demo problems I've done, I always, we're starting out with putting in a log problem, and then I keep motivating or promoting you into thinking of that as an exponential, as a way to explain in terms of an exponent, in terms of a power. And that's why we've always been having this running behind the scenes throughout the whole time. Okay? And so now, in that way, I'm saying this other statements on the other side, on our other part of the equivalency right here. The whole thing is an equivalency again. Okay? So we already nailed down how we call this one statement. It's an equation in logarithmic form. So what about this other statement? It's also an equation. Okay, it's also an equation. Okay, it's a statement, but we see that as an equation. So this is clearly an equation. Okay, but now I have to say it's in exponential. In exponential form. There, it's in exponential form. So you see, earlier when I began teaching about logarithm, I did introduce earlier. We are required to learn this lesson here, to learn about logarithm after we have learned about exponential function. This is why right here, you see, it has a close relationship. Logarithm has a close relationship with exponential expression that we've learned previously. All right, and so this form right here, see, base a raised to a raised to a variable y exponents. Okay, and that's why I'm saying that this equation here is written in exponential form. All right, so and nothing much at this point. And this is the first point where I show clearly my reason for requiring this lesson to be learned strictly after you have learned about exponential function, because this is the first connection, the first close connection I want to point out. And so here it's just simply, it's really one thing, one equivalent thing. Okay, these two statements are equivalent, but in one way you can say y is the answer, the value, the quantity y is the answer to that question. What power of base a to equal x? What power is that? Power y. Okay, so y is the answer to that question. And so now, as another way to equivalently say, we can equivalently say base a raised to the power y equals x. See, two separate statements. And this statement here is written in a form of a logarithmic form. And then this statement right here, the equivalent version, okay, but the logically equivalent version, but written in as an equation in what's so-called exponential form. All right, so I point this out for a reason. Okay, so let me now bring you in some further examples to strengthen this understanding. That's all. Okay, to enforce this understanding, because once we understanding and be fluent enough with this, it will become it will make our later learning go smoothly. All right. So now let's look at example 5. All right. So example 5 here has a really, maybe for anyone the first time, and of course I shouldn't have to say this, but for anyone being the first time learning about logarithm, then this instruction, this worded instruction may seem quite strange. Okay, so we want to rewrite. We want to rewrite the equation. Okay, we want to rewrite the equation in exponential form. That's the worded instruction of that, to rewrite the equation in exponential form. Okay, and then let me underline that. So that's the instruction made right now at this point, without seeing any actual problem being placed down. You have completely no idea. Okay, so let's hold on to that. Okay, let me now finish writing down one problem right there, one equation, and then we will understand, we will have a more clear understanding. Okay, so question part A right here. So now I give you an equation as following. Log base 5, or let's even forget about the word equation. It may make you think about solving an equation or anything like that. That's not the point. How about right now it's just simply a statement, and we write a statement as an equation. That's why I use the term equation like that, but think of that just simply a statement. So we got the log base 5 of t equals k. Okay, log base 5 of t equals k. Log base 5 of t equals k. That's one way I'm saying it. It means, hey, what power of base 5 to equals t? The answer is k. Again, what power of base 5 that equals t? The answer is 5. The answer is k. Okay, so we got one statement in the form of question and answer, question and answer. And so now all together, I see this one statement here as an equation. That's why it's an equation. Equation, equal signs, left and right. All right, we're not solving for any value. We're not solving for any variable. The instruction says, hey, this statement's written as an equation here. Let's rewrite that equation in exponential form. All right, in exponential form. So that means, just think about this. See, we're going to utilize this understanding that I pointed out earlier. That's all there is. Okay, we're going to rewrite that. So it's pretty straightforward. You see, right from here, the standard structure over here, the equation we currently have in our example is, in other words, this is currently in logarithmic form right here. See, so if we need to underline that, so do it. Okay, this is already in, this is a logarithmic form. All right, this is in logarithmic form. But now we want to rewrite the equation currently in logarithmic form into exponential form. So now the meaning now, see, so it's just a matter about we rearrange. So this is the base. This is the base. That's the number we want. Recall from that explanation I've had way at the beginning. It's all about what power of base 5, what power of base 5, okay, to equals t. What power of base 5 equals t. See, that way of how I explained in the beginning, it's always having a place to explain for any of the work we're doing here. What power of base 5 to equals t. This is all that question. That one question. But then we have already found, this statement here already gave us the answer. The answer to that question, what power of base 5 equals t? The answer is k. All right, so that means we put the k here. We put the k here. All right, that means we put the k here. So now deleting out the box. Now deleting out the box, okay? So now I have just, ladies and gentlemen, I have just rewritten my equation from logarithmic form into the final form right here. I call that exponential form. That's how I'm doing it. All right, and so as far as the thought process, once again, lay down that question that I used right from the beginning of our lecture here, of our learning here about logarithm. Use that as your driving force, as your driving key right there. All right, so we've got one problem nailed down. We have successfully rewritten a statement or an equation in originally logarithmic form to exponential form, to another statement as an equation but in exponential form. Okay, so this statement means the same as that statement, 5 raised to power k. See, because k was the answer to that question. So now 5 raised to power k equals t. All right. Let's now look at part B of the example 5. Okay, so here comes another statement for us right here. Another logarithm statement right here. So log, no base indication, equals 5. Okay, equals 5. So what I see, the way how I see it, just log base 10. Okay, common log. So log base 10 of r equals 5. Okay, log base 10 of r equals 5. And again, yes, this is a statement in the logarithmic form. We see this statement here written as expressed as an equation. So another way of saying this is originally an equation in logarithmic form. In logarithmic form. Okay. This is in log. An equation in logarithmic form. All right. But now we want to rewrite. We want to rewrite this equation into the exponential form. Okay, so this statement means logically means the same as. All right, so once again, for anyone who is the first time doing this, I'm trying to lay down the thought process in the most step-by-step way here. again, recall from that way how I explained. A logarithm, okay, a logarithm on this side of the left-hand side right here, a logarithm symbol or notation means it's a question. We want to find out, see, base 10. So we want to find out what power of base 10, okay, what power of base 10. What power of base 10 equals R. What power of base 10 equals R. What power of base 10 equals R. All right, what power of base 10 equals R. So now this number 5 on the other side of the equation is the answer. It's the answer to this question. This is a question and we've had the answer already. That means another way of saying 10 to the 5th power equals R. So now all of a sudden we realize we have arrived at another statement, an equivalent meaning, a statement in the same or equivalent meaning. But we say that this is our statement, our equation. It's an equation, okay? It's an equation. But this is now in exponential form, all right? It's an equation in exponential form. That's what it is. All right. And so the next one here, we should be able to pick up the pace even more. All right. So let's look at part C of the example. Okay. So how about we're looking at natural log of W equals N. Natural log of W equals N. So again, this currently is an equation in logarithmic form, right there. Okay, and we want to rewrite that equation, okay, in exponential form. Okay, so we want to find the other equivalent logical statements of that. Okay, so now I don't think we have done this often enough. I don't think I have to keep underlining that. So this statement here in currently logarithmic form, it says a log base e. Natural log means log base e again. So base e, okay, base e of log base e of W equals N. But see, before the equal sign, okay, this logarithm notation means it's a question. So think of that as a question. So like I said, what power of base e that equals W. So I write W here on the other side of my equal sign there in my statements. What power of base e that can equal W? Okay, and the answer to this logarithm, the answer to this question is N. That's why equal N right here. It means it's the answer to this question. So now the answer there is N. All right, so now deleting out the box here, all of a sudden, putting it all together, I realized all of a sudden we found that equivalent statement in exponential form here. That means equivalently to that statement, we're saying base e raised to power n, or base e raised to exponent n to the n exponents equals W. Or the nth power of base e, equals W. So ladies and gentlemen, again, this is it's the logically equivalent statement with that, but now it's written in an exponential form. Okay, so now this is the exponential. All right, exponential form. That's how we do these problems. All right, that's how we do these problems. Okay, so now as soon as we're ready for that, before I close down this example, before we leave this example, let's do an FYT. And so at this point, I believe with 3 problems that I have led the way in this example 5 right here, with 3 problems that we have done already where I led the way right there, you should be able to pull one problem through completely on your own right there, independently. So FYT. And after writing it down, feel free to pause the video, okay, and spend as much time as you can, okay. So log base 10 of V equals T. All right. So pause the video, spend your time looking back at the earlier steps and see how you can rewrite this equation as an equation in exponential form. All right, so at this point, assuming you have already spent some time, you may have even paused the video, right? But assuming you have already spent some time, that other equation, that logical equation that's equivalent to this, okay, in exponential form is going to be 10 to the t equals v. 10 to the t equals v. Power t of base 10 equals v. That's the answer right there. And that is an equation in exponential form. Exponential form. All right. And so now, we're still along this understanding where we can write an equation in logarithmic form into exponential form. We can also do the other way around. Okay. So just like that, a lot of time we have a statement, and this is again further enforce that understanding that it is strictly required that we've learned this lesson after you have learned from my earlier lesson about the exponential functions. Okay. Because now if we connect back to what we have learned from exponential function, then a lot of time we have an exponential statement right there, an exponential equation. Say we have something like this. We can have a statement that says an e to the x equals 5. This statement reads power x of base e equals 5. Okay, but it's an equation now, but it's in exponential form, and we want to find our way. We want to bring our way to rewrite this equation. We want to rewrite this equation as in logarithmic form right here. And so the standard structure that shows the equivalency is still here. Okay. So now I'm not going to dive into this quick little ones. Let's bring all of those problems in one further example. So now we call this example 6 right here. We want to rewrite the equation but in logarithmic form. All right. We want to write any one of our equation in logarithmic form. Logarithmic form. All right, so now let's look at part A of our example. So now from our days, from our time learning through that lesson about the exponential function, there were times where we're looking at, how about just simply 4 to the x equals y. I mean, sometimes you can also see that back in our lessons about an exponential function, and we wrote y equals 4 to the x. This is what we've seen. This is what we have seen more, that we saw more commonly throughout our lecture when we learned about the exponential function. Y is a function, the 4 to the x. It's an exponential function, and that's why this lesson must be learned again strictly after you have learned about the exponential functions. But now another way of saying, see, 4 power x of base 4, power x of base 4 equals y, same meaning. So now either one of this equation, we want to rewrite that in logarithmic form. We want to rewrite this into another equation in logarithmic form. All right. And so now going opposite, maybe a little challenge for anyone. But see, here's my recommendation. Tackle down right on the base. Tackle down right on the base. Okay, tackle down right on the base right there. And immediately when you see that base, then we can generate a log. So now it's base 4, so log with a subscript 4. That's the first thing we can tackle it down right there. Okay, that's the first thing we can tackle it down. And then, in my experience, then we're looking at, now, I'm going to hold on to that power actually. This number on the, see, from our beginning equation, the number on the opposite side, up and opposite side, I mean whichever the side that's opposite from the base like that. Here the base indication is on the left hand side, so on the opposite side is here. This y, I actually put it inside of our logarithm. Okay, that's the experience that I've done with that. That's, throughout my years, I did that. In that way, how I do it, I keep track of myself and made myself successful when I was a student. And I believe when I went on and became a teacher, when I taught that method, a good majority of my students caught with that and became successful with that way as well. Okay, and then, so that there equals x. Because the way, think of the way it reads now. If we think about, hey, with base 4 here, what power of base 4 equals x? What power of base 4 equals x? The answer is, what power of base 4 equals y? Okay, what power of base 4 equals y? What power of base 4 equals y? What power of base 4? Log base 4, okay, equals y. So we have this, but the answer to that is x. That's why I'm setting this up. Okay. All right, so we got one problem down, and yes, this is the equation that's written in logarithmic form. All right, where the start right here is in exponential form. All right, so you have seen a certain routine already. Let's continue. Okay, let's continue and repeat our routine there on another problem. All right, so here we go. I call this now part B right here. So how about 10 to the A equals B? 10 to the A equals B. All right, 10 to the A equals B. So there's a base here. Raised to a power equals B. Okay, so now in that routine I said earlier, hopefully it helps. Tackle down immediately into the base right there. So it's a base 10, so that means I'm going to go log base 10, but it's base 10, so we can skip the subscript 10. All right, and then in what I explained, in what I pointed out earlier, the next step is to recognize the number on the opposite side of the base. So the base is here, the number on the opposite side, that's the number we put in the parentheses. Okay, and then that remaining number in the power right here, we put it on the opposite side. That's how it is. So sort of like 3 little steps for anyone. But then here's the logic again. Think about that question I keep addressing. Think about this whole question right here. What power of base 10? What power of base 10 that can equal B? What power of base 10 equals B? The answer is A. The answer is A. What power of base 10 equals B? What power of base 10 equals B? That's how we formulate. So from that question, we formulate it into the logarithm symbol. What power of base 10 equals B? The answer is A. From that writing right there. That's why I wrote A on the opposite side. Okay. Question and answer. Question and answer right there. All right. So now, but all of a sudden, sitting back and looking at it, we realize that this is an equation. It's an equation in this is in logarithmic form. All right, it's an equation in logarithmic form. That's how we have done another one. All right. All right, so, and let's practice our routine here again with another problem. So here we go. I call that part C right here. Okay, so how about e to the h equals k? All right. This is an equation, a statement written as an equation in exponential form originally. Okay, it says base e raised to the power h equals k. Okay, base e, so that immediately when we have to write the equation here in logarithmic form, we're going to have to use log base e. But log base e is formally the ln symbol, now the ln notation. Okay, log base e. And so now log base e, and then, so that's step 1. Step 2 here is to locate that number on the other side of the equation and put inside the log. So that's step 2. We put the k here. And now I'm going to set up an equal sign. That h right here is going to be on that side. All right, so log base e, or natural log of k, equals h. Okay, so once again, logically speaking, here's how I see it. The statements, the way how it is, e to the h equals k, but think of that question that I was using to demonstrate the idea of logarithm. Base e, from base e, what power of base e that can equals 8? What power of base e that can equal 8? What power of base e, and that's why I'm using log base e, to equal 8, to equal k right here. I might have said h earlier. If it was, I apologize, but what power of base e to equal k? Okay, and so what power of base e, that's why we have this symbol right here, to equal k. So all that here is a question. And then the answer to that question, what power of base e to equal k? The answer is h. The answer is h. So that's why I'm writing that. This is question, so the answer is, we write it down right here. So now natural log of k equals h. All right, so this is the final answer. It's an equation. It's an equation, but it's in logarithmic form. All right, logarithmic form. Okay, and so now before I leave this example 6 right here, let's look at an FYT right here. So, and after 3 problems that I've led the way right here, I believe anyone learning in this lesson is confident enough to try one problem independently. All right, so now our FYT. How about e to the y equals x right here? This is an equation in exponential form. Okay, so go ahead and pause the video, okay, and rewrite and think of your ways and keep repeating my examples over and over until you click with your own route as well, okay, with your own explanation to come up with the correct final equation, but in logarithmic form. All right, so at this point, assuming that you have already paused the video if needed, right, and then have you spent your time thinking about this. So your equation in logarithmic form should be the following. Natural log of x equals y. Okay, natural log of x equals y. And since this is an FYT, allow me to skip the explanation. That is our final answer right there. All right. This is in logarithmic form. All right. All right, so we went over a good amount of examples, a really good amount of examples about being able to interchangeably convert between an exponential in logarithmic form to the equivalent equation in exponential form, and vice versa. An equation from exponential form to logarithmic form here. So we learned that skill throughout the 2 examples 6 and 7. Okay. For good purpose. I didn't bring those in for nothing. Okay, I didn't bring in those, and no instructors would bring in those 2 examples. Those 2 examples in example 5 and 6 earlier that we've done are very standard in any pre-calculus textbook. Anytime it comes to learning about a logarithm, very common. Okay, very standard. So I teach those. Any other professors in the past and currently teaching at the same time will do the same way, and in the future as well. Okay. And any one of us, the instructor brings in those 2 examples there for a good reason. Okay, we didn't bring it in. We didn't teach anyone learning that kind of example for nothing. So here's the good impact, a quite direct impact. And after seeing this, it further emphasizes that it is extremely important that you watch this lesson, that you view this lesson after you have viewed after you have learned about what an exponential function is. What an exponential function is. And so at this point, as after I have mentioned so many times, if you know that you have not seen or have not mastered your skills in the exponential functions, then feel free to exit out or take a pause on this lesson at this point, review your understanding or learn make some formal learning to your exponential functions, and then we're going to proceed with this lesson here. All right. But other than that, provided that you've already fluent with your exponential understanding, exponential functions understanding, then let me show you, or let's see how this understanding where we're able to change interchangeably the switch between equation in logarithmic form to equation in exponential form. Let's see how that can bring in as an application to our exponential equation, exponential functions understanding. Okay. All right, so now allow me to put in the following demonstrations. Allow me to bring in the following demonstrations right here. Okay, so let's look at the following. So again, assuming that anyone has already learned about an exponential function. So we know so clear, we know at this point clearly enough what this is. This is an exponential function, 10 to the x. Base 10 raised to exponent x. Right there. And the rule of this function here is that for any input x, right there, we're going to raise base 10, constant base 10 to that x power, okay, to that input being, to that x power being the input of our function. Okay, and then after you have also learned in all details about the function, you're also familiar with the graph of any of this exponential function. We know that it's a base, it's a positive base greater than 1. So now on my graphing space with decimals right here, allow me to quickly show the graph of this exponential function. All right, and of course, so this is the graph for our exponential function. F of x equals 10 to the x. Okay, f of x equals 10 to the x. All right, and I had to put this in a scale, a zooming scale other than the square scale, so that I can see somehow a good complete picture of the graph right here. So the vertical scale right here is not really the equal scaling with the horizontal scaling, and by the way, I have hidden all of the numerical scaling here. So all we need to understand is this is agreeing with our understanding about the graph of an exponential function where it's rising from the left to the right one way, and that intersection right there, that y-intercept right there, is at 0, 1. All right, but now at the zoomed out level, we want to do the following problem. Okay, so now I'm going to put in a line. All right. Now I put in this line in dotted black line right here. But the question now is that, so here's the graph of our function f of x equals 10 to the x. The point now is that we want to find out which x values, and that's the reason why I completely hid away all of the numerical values on this line right here. Okay, so that we want to, the point now is that we want to find out which x values. So this line here is at height 1500. As you can see, it's popping out right here. So this line here is y equals 1500. Okay, this line here is y equals 1500. So there's that intersection point. So right now my graphing utility kind of quickly estimated that. Okay, so that intersection point between the line y equals 1500 and our graph right here, that intersection point, we want to find out. But if we simply look at this value, then I consider that as cheating, because that's only estimating, that's not exact. We want to now find a solid method. We want to come up with a way to tell as a solid answer, not as an estimate, that what this x value is. So in other words, we want to find out at which x values that this graph in red will cross or will intersect with this line y equals 1500. All right, and so in that way right there, it's intersecting, of course, at the intersection point, the horizontal line here and the graph will have the same x values, but then we want them to both meet at the y value 1500. And so in that reason right here, we come up for ourselves, so to find x satisfying our function. So to find x, we want to find x. So it looks like in my explanation right here, we want to find x satisfying, okay, satisfying the graph of the function 10 to the x has output equals 1500. So that's now how we're writing that in written form as a written statement. That we want to find x satisfying our function outputs 10 to the x. See, vertical, going vertical value right there. And I demonstrated that on the graph. We want that to equal 1500. And so 1500 is represented graphically by that horizontal line, right, way above right there at 1500. But what we have here, all we do is, so, I mean, sitting back and looking at this statement now, we realize we have produced for ourselves an equation. And then primarily look at the instruction here. We want to find x satisfying. So isn't that clear that we actually indeed, we're looking for a way to solve this, okay? It's a little early, and it will come to a formal lesson later on, but here we call this, it's an exponential. See? For short, we call this an exponential equation, because the equation here involves at least one exponential term right there. Okay, this equation involves one exponential term. So we want to find the value of x. Okay, now we want to find the input value for this function that satisfies the function's output to equal 1500. So that's why, as I was saying here, we want to find x satisfying this. But that really means we just want to solve for x. Okay. But now another way of seeing now, so how do I blend in that understanding we have just discussed about right before I bringing up this exponential equation or anything like that? In the way how I see that, in the way how I see it with the understanding we have just learned, this is an equation, a statement in exponential form. It's an equation in, okay, it's an equation, this is an equation, okay, in exponential form. That's, okay, see, this is an application of what we have just learned right before getting into this. So now we realize that the equation we look for here, the equation we're looking at here is an equation in exponential form. Okay, and of course, the goal of this equation is to find out the satisfying x that makes the left-hand side equal the right-hand side. But for now, let's not worry about the goal there. Right here, seeing this equation as an equation in exponential form, as I have just stated clearly and out loud, okay, then with our understanding that we've gone through in example 5 and example 6 here, particularly example 6, okay, then here's how example 6, the skill we've learned from example 6 is useful over here. This equation in exponential form, 10 to the x equals 1500. It means, see, this is understanding that we bring in right from example 6. This equation in exponential form means the same thing as, okay, log base 10. See, because now I'm going to, and when I mention about example 6, I mean we bring in that skills, how we can rewrite an equation currently in exponential form into an equation in logarithmic form. Okay, so what it says now in this equation, see, and in my explanations, base 10, I write log base 10. Okay, base 10, log base 10. Okay, so in log base 10, we skip the base. And now that value, 1500, I put it here. See, that value on the opposite side of the equation, I put it there. Okay, log base 10 of 1500. And that will equals x. It's simply just a problem where we apply our understanding from example 6. We arrive at this. So right now I only need viewers or anyone who's learning in this lesson to see this as an equation in logarithmic form, a statement in logarithmic form. But now the way it reads, we were looking for what power of base 10 that equals 1500. That's why we had this question right here. What power of base 10, okay? What power of base 10 to equal 1500? We found our answer. Our answer is x. X is the answer to that question. So now, but then as the whole thing right here, the way it says x, we want to find x satisfying this equation. So now x equals log base 10 of 1500. Log base 10 of 1500. Now, let me switch over to the calculator. Let me swing by the calculator at my computer station here. Ladies and gentlemen, log base 10 of 1500 is something the calculator can provide for us. Log base 10 of 1500 equals 3.17609 and a lot longer. All right, 3.17609. So on my writing board, I'm going to say, to find that x value satisfying the output value of this exponential function to equal 1500, then the x values there has to equal log base 10 of 1500. But log base 10 of 1500 in real decimal values is about 3.17609 or 61. For this case here, how about I'm going to write it in 4 decimal places. So approximately 3.1761. Okay. What is the impact of this on decimals? We have answered our question. Right at that intersection point, we were looking for at which x value or at what x value will the output of this function, that's why it's written in red, it's drawn in red ink right here, in red color right here. The output of the function will equal the height here at y equals 1500. And so now we had that point earlier. See? Decimals already gave us that estimate 3.176. Okay, we went 3.1761. All right, and so now this is not only an estimate that we read out from decimals, but it's an actual value that we calculated using our understanding of the logarithm. Okay, so with our understanding from being, with our capability at this point in rewriting an equation in exponential form to an equation in logarithmic form, we can handle this kind of task right here. We can find an x value, an input value that causes our exponential function to reach a certain height, to reach a certain output right there. All right, and so now from this point, let's let's head into example 7 right there. And so another way of wording this, see, solve for x. See, given an equation, solve for x. All right. So now, to get into example 7. But before I formally call that solve for x, making it look so like solving an equation, then I'm avoiding using the term solve for x. That makes the viewers feel that we're working on an equation. But we just want to point out that this problem here as an application. So in example 7, I just want to stay as close to how I explained that on the other board right there. We want to find x. Find the value of x satisfying. Okay, satisfying what? We want to find x satisfying. How about question number 1 right here? E to the x equals 12. E to the x equals 12. Okay, e to the x equals 12. So the way how I want viewers and learners who learn with me, viewers or students who learn with me in this, I don't want you to see this as an equation that you solve for x. I don't want you to see this as an exponential function. I mean, as an exponential equation that you are solving for x. That's a little too rushed right there. All I need you to understand is, yes, we have an equation where it's written in exponential form, but it came out from the following problem. We have, and allow me to skip swinging by the graphing utility with decimals. E to the x has some graph that you have learned from your exponential function. Okay, 0, 1 is here. And of course, allow me to be upscale or whatever. But we want to find out, this equation is all about, this work we're doing is all about, we want to find at which x value, okay? At what x value, we want to find that x value where our function, our e to the x as an exponential function, outputs hits to 12. We want to find out at which inputs will cause this e to the x function to equal 12 as the output. That's what I want, students of mine or anyone viewing the lesson here to see this equation as in terms of an application. And then we will have all our time later in a separate lecture to learn about solving different exponential equations. And there I'm going to have more freedom using the term exponential equations. Right now, yes, it is an exponential equation. But again, I want you to see this as simply an application problem where we specifically, after we learn about what an exponential function is, it has a graph like that because the base is greater than 1. Okay, and then we just want to find out, hey, at which inputs will we reach our function output to be 12? That's all there is. Okay, and so because we serve that goal of ours, to look for that input, we produce for ourselves this equation. Okay, because we need to serve that goal right there, to find that input, we produce for ourselves this equation. And yes, if you see that as an exponential equation, yes, I agree, but like I said, let's not think of it that way. So now with this equation currently in exponential form, okay, and I'm not going to worry about finding x. I'm just going to, anytime we see an equation in exponential form, let's rewrite it. So it means this equation currently in exponential form, it means we can do the following. Base e, so log base e of 12 to equals x. All right. But now after successfully landing into the logarithmic form of our equation, then all of a sudden we realize all we do is just throw this value into a calculator, because the way it reads right now, log base e of 12. And that is our answer for the x. To find that x value satisfying e to the x outputs to equal 12, that x is going to be found by running this value from the calculator. Natural log of 12. Okay, so that now means before I swing to the calculator, I'm going to just get that prepared. All right. All right, so now on my calculator screen right here, natural log of 12, ln of 12. Okay, now let's hit enter. So 2.485, rounded to 3 decimal places. Okay, 2.485. All right. So now the answer is x is approximately 2.485. Okay, 2.485. All right, and so we can also check ourselves. We can also check our work right here. I mean, it depends on different situations. Sometimes an equation is so easy to solve, we don't have to bother checking. This equation here, it has some concept. It has actual applications, and so that's why let's check for it. See, the point now is that we want, if this is the input, at least we want that to come close to, we want the function's output e to the x to come close to 12 like that. So if f of x equals e to the x, then f at 2.485 must be e to the 2.485 like that. Okay, e to the 2.485. And so with the calculator here, e to the 2.485, okay? Our outputs does get to 12 and close enough to 12. And of course, because we found that answer earlier only as an approximate, so now look at the answer right here. If we use this as the input right here, our exponential function e to the x will reach to the height being really near, really close to 12. All right. And that's how we know we have found the correct x value satisfying this, the function output for e to the x to reach 12. Okay, and so now once we have had it in that way, and we see that it's directly apply that skill we've learned from example 6 right there, where we are able to rewrite an equation in exponential form to an equation in logarithmic form, and then from there we just punch in the values, and that's how we get the value for x. All right, so let's now head out for a couple of other problems there. All right, so now part B, I'm looking at, we want to find the x value satisfying 3 to the x to equal 0.015. 0.015. All right, so now 3 to the x equal 0.015. Once again, the whole purpose, I don't need anyone to see this as we are solving an exponential equation. It's making it way too heavy of new thing to learn. Right here in what we have just learned already, we applied our understanding from example 6 right there earlier. That's all. We want to find the value for x satisfying the exponential function 3 to the x to reach output 0.015. That's all there is. We just want to find an x values, an input value that causes our exponential function 3 to the x to reach this output 0.015. Okay? Again, as a demonstration, 3 to the x as a function, as an exponential function, has a graph rising from the left to the right because the base is greater than 1, asymptotic to that line, to that x-axis right here. So we want, and then this value right here is a 0, 1. So I want the height to be 0.001, a height really low down here. Okay, so 0.015 is down here. So we want to find out, hey, what x value is that making my function reach down to that height only a 0.015 right there, way below 1. And that's the reason why it sort of explains why I put the x that we are tentatively finding on the left-hand side of the y-axis. See, all of the details you've learned at this point comes together and makes sense. All right, so, but now that's just the explanation. Really getting into the work. I see this formulated as an equation in exponential form. The equation in exponential form. So now in my step, all I do is apply our experience from example 6 to rewrite this equation into logarithmic form. So into logarithmic form, this is base 3. So I'm going to go base 3, log base 3 of 0.015, and all that here will equal x. Log base 3 because it's the base right there. And so with all that experience I've learned, and I've pointed out all of the details I've known, all of the experience I've done throughout my years in example 6. So now allow me not to explain too much about those. But this equation now can be rewritten as log base 3 of 0.015. Okay, I realize this may be a little hard to read right there, 0.015. Okay, log base 3 of 0.015. And so now this is an actual value that we just realized it's an actual value that we can actually just hop over to the calculator and pull out a value for that. Okay. So now on my graphing calculator, on my TI calculator right here, it's a log base 3. So more practice for us in terms of working with a log other than base 10 and base e right here. So I can choose with the natural log. So it's now I'm going to go natural log of 0.015. Okay, and I'm dividing that by natural log of 3 because 3 here is the base 3 for our logarithm problem, for our actual logarithm problem. Now hit enter. The answer now has to be negative 3.823 here once I round to 3 decimal places. But again, rounding to 3 decimal places is only my own rounding in that I decided for this problem right here. In other problem I may decide differently, and when you are anyone doing your own problem, make sure you watch for the rounding requirements there in each of the problems you're doing. Okay, so here I round to, let's just round to 3 decimals. So negative 3.823. All right, so now I found the answer. X has to be approximately minus 3.823. All right, and for this particular problem, let's be flexible. I still have the graph here, and so I can tell it's consistent with the fact that the answer has to be somewhere on the left-hand side of the y-axis. So now let's look at the answer. All right, and it goes far enough. So here the calculator made it clear that it has to be nearly -4, nearly -4, -3.823. All right, and for this problem, since we still have the graph there, I don't think we have to put this answer as an input into our exponential function 3 to the x to make sure we come up to somewhere near 0.015, even though you are more than welcome to do so. Okay, let's now head out to the same example, problem C right there, part C of the example. All right, so in problem C of the example, how about let's look at 10 to the 2x minus 1, and that equals 5,000. That equals 5,000. We want to find x satisfying 10 to the 2x minus 1 equals 5,000. All right, and so let's make a recall here, but somewhere in my teaching and somewhere in your learning about the exponential functions earlier, prior to viewing this lesson right here, I introduced that a function like this, base 10 to raised to a 2x minus 1, it is clearly it is officially considered as an exponential function. Okay, it's an exponential function, and so that's why after I pointed this out again to remind you from our understanding of the exponential function, then clearly this problem is again this function as a graph, base 10, so it's going to have a graph rising one way from the left to the right. Here's some intercepts, okay? And you can apply your own understanding from the exponential function into finding the y-intercept here. I'll leave that for you. But now, I am sure that the y-intercept here has to be much lower, okay? Much lower than 5,000. So 5,000 is a line way up here. I'm very sure. It's just I didn't bother doing the actual calculation here, but I'm very sure that this y-intercept is much lower. And so now in that point, in that way, we want to find a value for x, that's the value for the input that cause our functions to reach output value being 5,000. Just that explanation again. And so in this way right here, in the way how it is for the graph, base 10 greater than 1, it has to be rising from the left to the right. So that input, once we have found, it has to be to the right-hand side of the y-axis. Okay, so something to kind of know ahead of time before we head in to actually do the problem. All right, but now with so much reasoning, again, back to that problem, it's to find this x satisfying, whatever that is, we have produced for ourselves an equation. To find the x satisfying this, we have produced for ourselves an equation in exponential form. In exponential form. All right, the only scary thing a little bit, the only scary part a little bit here is that this exponential part right here is a little more complicated than the usual case right here. Usual case is just one simple x. Here is a linear expression of x. Okay, but let me show you. That exact experience from your example 6 is going to carry in as is. Okay, you're going to take the exact experience, apply that here, one by one. Okay, and here's how it works. And go as closely as possible with everything we have done in example 1. So this is the power, this is the base, and this is the number on the other side right there. So here's how I see it. So from this equation currently written in exponential form, I can rewrite that according to example 6 that we've done. I can rewrite that as, how about log base 10? We skip the base, so log only, right? Log base 10 of 5,000. That equals, okay, but not equals x. It equals 2x minus 1. So the entire expression here, 2x minus 1, is equated to log base 10 of 5,000. Okay, the whole 2x minus 1 is equated to log base 10 of 5,000. All right, and so all of a sudden we realized this log base 10 of 5,000 can be obtained from the calculator. Okay, and so now there are two routines, but to make it easier for viewers, we can do the following. First, let's use the calculator to obtain log base 10 of 5,000. It's a value that we can calculate, log base 10 of 5,000. Now hitting enter, this is our answer. Okay, and again, allow me to round this to 3 decimals. So it's going to be 3.698, I mean 9. So 3.699, okay, 3.699. So, and of course it's not exact, so it's only an approximate. 3.699, what comes out from the logarithm base 10? The log base 10 of 5,000. And then we realize this answer is not going to be the answer for x. This is the answer only for log. This log base 10 of 5,000, but this log base 10 of 5,000 is equal to the 2x minus 1. It's equal to the 2x minus 1. So this is the easy, I mean, it's easier round to understand, but it's not necessarily the shorter round. Okay, but I just want to show directly that any time that we realize we can do the immediate calculation of the log value, here we go, just do it, and then it may equal to something else other than simply just an x. But now we can continue proceeding into finding x, solving for x from here. Okay, and then yes, it's a little bit strange that our equation starting from this point turns out to be a nearly equal sign instead of exact equal sign. But it still works, exact same logic right there. So now I'm going to add 1 to both sides, okay, making it now 4.699, okay, to approximately equals 2x. All right, and then I'm going to divide both sides by 2 on both sides, even though the equation sign here, the equality sign is only an approximately equality, okay, an approximate equality. Okay, dividing both sides by 2, so I'm ending up with my final answer here. So x is approximately, and now since things are going all approximates, I need a calculator again for this last step right there. All right, so 4.699 divided by 2, okay, that's now 2.3495, and here let's leave that exact like that. Okay, because it's exactly half of this approximate 4.699. All right. So that means our answer for x here, the inputs for x has to be approximately 2.3495. All right. Okay, so positive 2.3495. And again, legally speaking or officially speaking, I have to put this value as an input into this function and then do a formal calculation to ensure that the output value of this exponential function will reach or arrive at 5,000. But since the picture is still here, you can see that, and I made it clear that it makes sense that the x value should be somewhere to the right hand side of our y-axis, simply because the graph itself of this 10 to the 2x minus 1 is a rising graph. I don't need a graphing utility to know for this. Once again, all of that understanding is from our understanding about the exponential function. It's a base 10 greater than 1, so the graph has to be rising one way from the left to the right. Okay, and then with this y-intercept right here, as I mentioned earlier, I am very sure that the y-intercept, even though I did not do a formal calculation here, I am very sure that the y-intercept here must be way lower than this value 5,000 on the y-axis. And so that's why, in order for the graph here to reach that value, the x value, the inputs to reach there has to be somewhere to the right-hand side of our y-axis. All right, and so in that way, let's look at the consistency. It looks consistent enough right there, okay? As far as something to check for consistency. Okay, and then if you would like to look for even more detail in your checking solution, then yes, you can go ahead and substitute that into your your function, your exponential function, 10 to the 2x minus 1. All right, so that's how we have done part C of the example. All right, so now let's look at part D of the example. Okay, let's look at part D of the example. Okay, so now we're going to look at 3 times 1.06 to the x, okay, and equals 180. Okay, 3 times, so the way it reads now, 3 times 1.06 to the x. So this is, so what, in that logic I've been explaining, we're still looking at that kind of problem where on one side we have an exponential function. On one side of our equation, of our statements, we have an exponential function. That's on the left-hand side here in this problem. On one side, we've been having an exponential function on one side. And then the whole goal of the problem is to look for an input x that's satisfying our output of the exponential function to reach that much on the other side. That's another generality of these problems that I brought up in example 7 here currently. Okay, and then again with this function here, with this exponential function here known to have a base greater than 1 already, right? And then the exponential function itself is only just base 1.06 to the x. This is only a coefficient 3. So with your understanding, and again, allow me to assume that anyone viewing the lesson here has already learned the exponential function. Then we know that this exponential function here has to be, again, a graph that's rising from the left to the right, okay? Vertically, rising from the left to the right. And then for this particular problem, you can use your own experience after you've learned about the exponential functions as well. You can apply your own understanding to verify me here that this graph will have a y-intercept right at 0, 3 indeed. 0, 3. Okay, so how do I know that? You have your answer there. You will have your answer after you have already learned throughout my lecture on the exponential functions. Okay, and now, so the reason I point out about the y-intercept here, because now once we know where the y-intercept of this graph is on the y-axis, then it is clear, so clear, that the value 180 is way above this line. That means in order for this graph to reach that height vertically, we need to find out what that x input is. But further, the x input I know for sure has to be somewhere to the right-hand side of the y-axis. That's how it's done. Okay, I mean that's how we lay down our thought, our thought process like that. Okay, so now, but as far as getting into it, now, yes, this is an equation. It has exponential form. It has exponential function involved. Okay, but I wouldn't rushly say that this is an equation in exponential form yet. I wouldn't rushly say so. So my point is, don't rushly apply the experience we have done in example 6 here yet, immediately first thing in line. Nope, because it's not directly, you see at this point now, if we have simply one exponential term, no coefficient, or coefficient 1 indeed, I should have used that correct term, coefficient 1, and then the exponential term, and then equal a value, that's where we can apply our understanding from example 6 to here to rewrite this equation currently in exponential form. This is also where I can officially call it equation in exponential form. This one is not quite yet, okay, because here's what's the difference between this equation and the one that I call in exponential form. We still have a coefficient other than 1 here, so we need to find a way to get rid of that. That's the logic that I use right there. Okay, and so now in that way, but with thankfully for any one of you who are in this course right here, you must have learned through an earlier algebra course. We can just simply divide 3 from both sides. Dividing 3 from both sides here will not change the exponents, the exponential components here. So it's only cancel away the coefficient 3 in front of our function. So now in the next step, we produce a 1.06 to the x equals 60. 180 divided by 3 is a 60. 3 cancel away. Now we are officially at what I've been calling an equation in exponential form. That's the one. Okay, that's the one. Okay, and so this is not directly relevant to that graph, but it's part of the step. This graph reflects this original equation, but this is one step where we made ourselves closer to the answer. Okay, one step we use to make ourselves closer to the answer. Now we're in that equation that's successfully in exponential form. Okay, and now we can do that. We can apply that experience from example 6 in here. Base 1.06, so log base 1.06. We have to. That's the base right there. Okay, and then we put 60 inside of the log. Okay, and then that will equals x. This problem is actually indeed a little better than the one in part C in the sense that we have just one simple x here already. After we successfully rewritten our equation in exponential form into an equation in logarithmic form. All right, and so now after this point, at this point right here, let's swing over to the computer and graph a value for this. Okay, and at this point you have had all of that experience how we can even use a calculator for any general log like this. Okay. All right, so now on my calculator here, on my TI-84 calculator, to calculate log base 1.06 of 60, I'm going to do the following. I'm more comfortable with natural log, even though you can also choose to go with the log base 10 right here. Okay, so natural log of 60, I'm going to divide by natural log of 1.06. All right, and hit enter. This is our value for that. This is the value for log base 1.06 of 60 right here. That's what it is, 70 point. And so in my decision of using 3 decimal places, then 70.266. All right, so that means now we have found out that x must be approximately equal to 70.266. All right, 70.266. Okay. So to keep the video from getting too lengthy, to keep the lecture from getting too lengthy right here, then I'm not going to formally check the answer like what I did in part A anymore. I'm not going to throw this into the exponential function 3 times 1.06 to the 70.266 to ensure we arrive at 180. We don't need to do that. I mean, I will not do that in the video here, but you are more than welcome to try that on your own to ensure that what we've done here arrive at something very close to 180. Of course, because we only chose an approximate. Okay, but at least right here in the lecture, I can tell that my answer that we came through the calculation is consistent with what I laid down earlier. The x value was already expected to be on the right-hand side of the y-axis, and look at our value right here, positive 70.266. Okay, so that's one way I can check for consistency right there. But then will that land precisely into 70.266? Well, with anyone, I'm quite I'm quite sure I follow all the proper steps like that. But you are more than welcome to do your own checking work on that to ensure that this is the input x that lands our function 3 times 1.06 to the x to equals 180. All right. All right, so now let's look at part E of our example. Okay, so our example has the following equation for us. So 100 minus 100 times 1/4 to the x, okay, equals 70. All right, so just like that, just like any of the earlier problems, one thing in common they all have. One side comes out as from an exponential function, and that's why it requires again that you gotta watch, you gotta learn from my lecture about what an exponential function is. This is also an exponential function, okay? And so we further learn that this function is in the form of a c times a to the x, okay, plus b right there, or plus a k value, constant term, okay, plus a k. It's an exponential function. Now in this form right here, our function here has base 1/4 less than 1. Okay, so ideally, theoretically, I'm looking for the following. Okay, we have a horizontal asymptote here at 100. Okay, and our graph is as following. All right. Then there's a y-intercept here. You can verify for me. You can go ahead and spend your own calculation to exactly know where the y-intercept is. But in the end, I'm very sure, and you can confirm this, that 100 is above the value for the y-intercept. Okay, and so now, and so of course with all that upscale, and I didn't have a formal calculation. I didn't really have a formal calculation, but I am firm that 70 has to be above the y-intercept here. So that means our x values has to be, we want our graph to reach to the value, we want our function to reach to the value 70. Okay, so 70 is here. We want our function's outputs, which appears to be in this form, asymptotic to that line y equals 100. Okay, and then I haven't done a formal calculation for this, but I can leave that for viewers, and it may be even lower or it may be even down below the x-axis. Not important, but I'm sure that it's lower than this line 70. And so that's making it the x value that we're about to find has to be to the right-hand side. Okay, has to be to the right-hand side. So and the shape has to be rising like that, but in the asymptotic way on the right end. Okay, so now, but then in the end, finding the x value satisfying this equation is not easy at start, because it doesn't look at all like those equations of ours that are in exponential form. It's way not in exponential form. Okay, it's way not in exponential form. So we got to find our way to bring it back to exponential form. Okay, to exponential form. But actually, it's not so bad from here. Okay, so again, here's how we bring in our past understandings about the algebra over here. The only, gladly, there's only one exponential term involved. That's here, and that's also another thing common to all of the other earlier ones. These are just constant coefficients and constant term. So looking for the whole exponential function to equal this output. So now on our way, as we are on our way, being on our way to bring this whole equation down to exponential form, I'm going to first start out by subtracting this constant term from both sides. Okay, and doing that, it will produce for me minus 100 times the 1/4 to the x. To equal minus 30. Okay, 70 subtract 100 is negative 30. All right, and then from this point on, I am going to, now this is a little bit more similar to part D that we were doing earlier. I'm going to divide both sides by that coefficient negative 100. So my resulting equation becomes, so the 100, negative 100 cancel. Now I have 1/4 to the x equals 3/10. Okay, 3/10. And 3/10, here we can write it as a 0.3, or it doesn't hurt to keep it as fraction. Either way it's fine. You can write 3 over 10 as 0.3 or 3 over 10. But now we are successful in, we have arrived successfully at the exponential form of our equation. At first, it's not exponential form, quite far away, but it took us only 2 steps. And I wrote down the steps here carefully. And that's how we took our way, we took our step to get to bring our equation at start down to being in exponential form. Then from here we can apply our understanding from example 6 to rewrite this equation to logarithmic form like that. All right, so the whole intention of problem from part D and E, and until now is that, a lot of times, quite often enough out there, that you are given an equation where it's quite not in exponential form. Then you have seen enough through 2 examples that we can use some algebra to rearrange that back to exponential form of our equation, first thing in line. And then we use that experience, we apply that learning we have had in example 6 to rewrite the equation here in logarithmic form. Okay, so now at this point, let me erase some part of my drawing here a little bit. Okay, so now it leads to, from that equation, actually I don't think I need to draw that line right there. So from that equation, now it's base 1/4. So now I go log base 1/4, okay, of the value on the other hand, you can write at 3/10 or 0.3. It's all going to work. And that there equals x. That will equals x. All right, and so now we are ready to type this into our calculator. Okay, and then the calculator, after running the calculator, it's going to get us at least a close enough approximation of that x inputs that we're desiring for. Okay, that we desire. All right. All right, so on my calculator, once again, we're working with a base other than 10 or E. So I'm going to go with, I have to apply with the workaround right here. So natural log of 0.3, and I'm dividing that by natural log again of 1/4. I can just type in 1/4 in parentheses. So use parentheses very carefully when you run with, when you're working with advanced calculators like this. Okay. All right, so now our answer is 0.868 rounded to 3 decimals right here. Okay. So now what it means, we have found our x value satisfying this graph reaching to the height being 70 right here. That x value has to be, now forgive me with a very narrow space right here on the board, but x to satisfy that equation, to satisfy that the graph here reach to that output 70 vertically, okay, then x has to be approximately 0.868. All right, and that is our final answer for that. All right, and so once again, I don't think I have to, in this lecture, again, to keep it from being too lengthy, I'm not going to put this input that we found into the actual exponential function here to check whether it will reach to equal 70. Okay, but I'm very sure it's going to be like that. You are more than welcome. Anyone learning in this lesson is more than welcome to do your checking work. But at least I can see things being consistent with the way how I draw the graph. The value for x we are expecting should be to the right-hand side of the y-axis here. That's the one thing I can check for consistency right there. All right.